Alright, so here is the start of our next chapter, which is all going to be about electricity, really. The first section we're going to talk about is electric charge and static electricity, though. So, let's first talk about electric charge. So, when we talk about electric charge of something, that is the property that causes the subatomic particles, remember those were protons and electrons like we talked about in our chemistry unit, to attract or repel. Okay, remember these protons and electrons were negative and positive charges. Okay. Now, an excess or a shortage of electrons is what produces a net electric charge. Okay. And we kind of saw this actually when we looked at ions, right? And we'll talk about those ions again. An example where a normal atom by itself, so like oxygen, is neutral. But when I was talking about the ion version of oxygen, oxygen 2 minus, okay, that actually has a charge of 2 minus now. So it has what we'll call a net electric charge. Okay. So this is what it's talking about when it says an excess or a shortage of electrons can produce a net electric charge. Which, remember, when we talked about those protons and electrons, okay, the electrons, remember, surrounded the positively charged nucleus. So like here is your nucleus, which consisted of protons and neutrons, which were neutral, remember, so it's positive. And then you had the electrons, remember, in no specific arrangement, right? They were just like an electron cloud, for example, okay? It's a rough drawing of an atom, but you know it works. But when we talked about neutral atoms, like we said, they had equal number of protons and electrons. So like if we're looking at, again, let's say just oxygen, that was neutral, okay? That has, where is it at? 8 protons, and remember 8 electrons, because it was neutral. But when we looked at the ion form of it, oxygen 2 minus, right? It still has 8 protons, okay? The protons never change. But in order for it to have a 2 minus charge, my electrons had to be gained, remember. So now it gained 2 more to be 2 minus, so now it has 10 electrons. Same thing goes for positive ions, remember, right? So let me erase my atom model over here. Get rid of that glorious model. If we're looking at like potassium, so K, right, that has 19 protons. I'll put P now for protons. 19 electrons. But potassium 1 plus, its ion form, has 19 protons still, but now it has 1 less electron. 18, remember. Okay. So don't forget that type of thing too with the atomic structure. So now when we talk about electric charge, okay, we can actually measure this, which we're going to measure it as a coulomb. Okay? And what a coulomb is it's 6.24 times 10 to the 18th electrons, right? So that is 1 coulomb. All those electrons are 1 coulomb, and that's how we measure electric charges, right? And to give you an example, like of how many electrons are in certain things, like everyday things, a lightning bolt, for example, okay, is actually about 10 to 20 coulombs of charge, depending upon how strong it is. And like a camera, that electric charge it uses is about 0.025 coulombs. So if we actually want to look at how many electrons are like in one lightning bolt, for example, to see like the capacity of how many electrons are, let's say a lightning bolt was 15 coulombs, 15C. And we're going to go back to this railroad type calculations like we did in chemistry. If we know 1 coulomb is 6.24 times 10 to the 18th, electrons, you'll take 15 times that. And in one lightning bolt, probably that you see every day, well, not every day, but when there's a storm out, 9.36 times 10 to the 19th electrons are in that bolt. So that gives you an idea of like how many electrons are actually in those things. And then now we'll talk about also, when we talk about electric charge, we talk about the forces of those electric charges, okay? So remember, when we talk about electric forces, okay, like charges repel. Like this is like a magnet, like you guys have all have seen before, right? When you put two ends of the same part of a magnet together, they repel. They don't attract to each other. While when you put the opposite charges together, the opposite ends of a magnet, they attract. So like that's saying if I want to put like a minus charge with a minus charge, they will repel each other, right? Same thing with positive charges. And then opposite, you only have a positive with a negative, they will attract, right? Like magnets, it's the same sort of force that you see in magnets. And we can also talk about the electrostatic forces, which is basically the force of attraction or repulsion between electrically charged objects. So let's say like if an object was actually charged, and I'm looking at the force between two different objects. And how we can actually look at this is this electrostatic force increases the closer charges are, right? Which kind of makes sense, right? The closer, like if you had two magnets again that are positive and negative ends, the closer they get, the more force of attraction they actually have. Same thing with the repulsion of it. The closer they get, the more repulsion they have. Okay? So that is actually a direct proportion as the forces increase as the closer those two charges get to each other. And also, we talked about gravitational forces last chapter. These electrostatic forces are actually much stronger than gravitational forces. Just to give you an idea of how strong they are. So again, looking at when we talk about the distance, right? In part A, we have the opposite charges, they attract each other. Okay. So if let's say if I double the charge on that actually, I also double the force too. So not only distance doubles the force, doubling one charge also doubles the force on both charges too because I'm increasing the amount of it, right? That's like if I had more magnets, I have more charge, they're more attracted to each other. Okay. So that's what part B is saying. And then C now is looking at that like charges repel again, okay? So now I have two like charges of positive. They're far apart, which means the force is about 1/4 as great as what I started with essentially. But it's just basically looking at the farther they are, the more repulsion, the less repulsion they have then. But when they get closer, they have more repulsion. Okay, it's the whole idea we're kind of looking at this graph. Okay, so now let's talk about electric fields. Okay, we talk about electric fields. Okay, the effect of electric charge has on other charges in the space around is what an electric field is. Okay, so if something has an electric charge on it, we're looking at how it affects other things and other charges in that space. Okay, that's what an electric field is, like a magnet again, going back an example, seeing how that electric charge from it affects the thing around it. Okay, and this electric field exerts a force on any charged object placed in that field. Like you see with magnets, right? If you put a magnet and you put a staple, a paper clip next to it, right? It'll have a force on that paperclip to attract to it. Right? That's what it does. So that magnet exerts a force. And the strength of this field depends upon the amount of charge it produces in the field and the distance from it, right? Which the larger charge, your electric charge you have, the more or the larger electric field it has. And same thing with distance, right? The farther it is, the less of a field it has. But the closer it is, the more like um, strength it has. Again, going back to a paper clip and a magnet, right? The farther the paper clip is from the magnet, the less effect that electric field has on the paper clip. But once it gets closer, that effect becomes greater and greater. Okay. And when we talk about positive and negative charges too, the fields are actually related to it. So if I'm looking at a positive charge, that field is always protruding in an outward direction, while a negatively charged field is always coming at an inward direction. Okay, so it's important you understand that a positive, that field is going outwards, while a negative, that field is coming inwards. So now let's look at static electricity and charge, right? You've all have experienced static electricity at one point or another. But static electricity is just a buildup of electric charges on an object. And like we've talked about before in last year, like the conservation of energy, we also have the law of conservation of charge, which is the same thing as energy, where the total charge in a system is always constant. I can never create nor destroy charge. Okay? Can't make it appear out of nowhere. I can't just leave it. But when there is a charge transfer, that total charge is always the same before and after the transfer occurs. Okay? That's what it's saying in the law of conservation of charge. But when you have this static electricity buildup, okay, afterwards you usually have what's called a static discharge. And this occurs is when a pathway through which a charge can move forms suddenly. And one you've experienced a lot is maybe like the shock from a doorknob or a shock from someone else. Okay? Like a good example, another example is like if you have socks on and you're walking around on a carpet and you move your feet really fast, you're building up static electricity. Okay? But that static electricity stays on you until you go touch something like, let's say, metal like a doorknob, and you feel that shock, or you feel a shock from another person, right? That's the static discharge occurring from the static electricity. So in order to have static discharge, you have to have that static electricity actually built up before. So we can also kind of look at this in relationship to like how lightning actually builds up, okay? So in lightning, charge builds up in the clouds from friction moving between air masses. So if you look at it, the top of the cloud, there is positive charge. So up here, there is a positive charge. Okay. The bottom of the cloud, there is negative charge, while the ground is what we'll call, again, positive. Okay. What's happening then is the air between these two starts to become charged. Okay. Once they become charged, that's where like the lightning forms. Okay. And that pathway for electrons to travel from here to here, and then essentially from the cloud to the ground, is what's lightning actually being occurred. Okay. So that lightning you see is actually the pathway of electrons from the top of the air cloud, basically to the bottom of the air cloud, and then eventually it's striking down to the ground because again, once it goes downwards, it's again there's another positive attraction occurring to the ground. Okay, so most of that we see actually goes up and back and forth in the cloud, but there are the rare occasions where if the cloud is closer to the ground, it'll go straight to the ground. That's what happens in a lightning strike. Now, to finish up, let's talk about the three ways quick that we can actually transfer charge or build up charge. Okay. One way is friction, right? And a good example you've all done before at one point in your life is rubbing a balloon on your hair, right? The electrons move from your hair to the balloon because the rubber actually has a greater attraction for electrons than the hair, okay? And that's why you see your hair stand up now because your hair is positive, your balloon is negative. So you see the electrons moving from your hair to the balloon, and that's what causes that electric transfer, the transfer of a charge. The second way is by contact, and a good example this is a Van der Graaf generator, which I wish we had one that you could actually look at, but what it does is charge is built up in this sphere, okay? And when you touch this sphere, the charge transfers from the sphere basically, whoops, to yourself, making you repel the object. So once the charge transfers from the sphere to your hand to your body, okay, you actually hold a charge now, which allows you to repel other objects, and that's why your hair stands up so crazy like that. And then the last way you can actually transfer charge, which is by induction. Transfer charge without contact. Okay? And this is going back to that carpet one I talked about, where if you walk on carpet, you build up a negative charge on your body, which repels electrons. And then once you build up that negative charge in your body, okay, before you even touch it, almost, okay, you feel a shock because that shock transfers from your finger to that doorknob, and that's where that static discharge comes from usually. That's why you usually feel it sometimes before you even touch it, okay? Because that doorknob is neutral now, but the charge within it has also moved. But that's electric charge and static electricity in a nutshell. Okay, there's not a lot of calculations with this part. Whoops. Okay. But the homework is going to be pretty basic. It's going to be a little worksheet that talks about explaining some things too now, but it'll be posted along with this video. So if you have any questions on that, let me know.